consisting of elements 1, 2, 3, then number of equivalence relations containing 1, 2 is. Okay. So let us first of all consider one relation at least, R1. Because there are three elements 1, 2, 3, it has to be reflexive. For equivalence relation, we have to find out the number of equivalence relation. So the relation we write here, the ordered pairs, then the set as a whole, this R1, it should satisfy reflexive, symmetric and transitive, all the three properties. For reflexive 1, 1, 2, 2, 3, 3 have to be there. And because 1, 2 is there, so 2, 1 should also be there. 1, 2 is there, then 2, 1 should also be there. If I stop it here, of course it is reflexive, and 1, 2 is there, then for symmetric 2, 1 is there. Is it transitive? Let's see. I look at it like this. 2, 1, 1, 2, 2, 2 is there. 1, 2, 2, 1, 1, 1 is there. So yes, R1 is an equivalence relation. So one R1 is there. Let me see if I can make more. R2, of course, 1, 1, 2, 2, 3, 3, and 1, 2 and 2, 1, because 1, 2 has to be there, so 2, 1 will also be there. What else can be here? We can include now 1, 2 we have taken, and so 2, 1, I can include 1, 3 also. So if 1, 3 is there, then for symmetric 3, 1 should be there. And because 1, 3 and 3, 1 is there, and it has to be symmetric also. So just look at symmetric part. See 1, 1, 3 and 3, 1, 1, 1 is there. In this, because it is 2, 1, just look at these two. 2, 1, this one. Look at 2, 1 and 1, 3. 2 is related to 1 and 1 is related to 3. So 2, 1, 1, 3, then for symmetric it should be 2, 3 also. So we have to include an element 2, 3 also. We should include the element 2, 3 also. And because 2, 3 is there, for this to be symmetric, then 3, 2 should also be there. So this is another, now it can easily be verified that yes, this is also an equivalence relation. And there is no other possibility for an equivalence relation on 1, 2, 3 with 1, 2 always included. So there are only two such equivalence relation R1, R2 possible. So your B choice is the correct answer. Now let f is a function from set of real numbers to the set of real numbers be a signum function defined as this, that fx is 1 when x is greater than 0, it is 0 for 0, and negative 1 when x is less than 0. That is one function f. And the other function g is defined as the greatest integer function gx. You already know what is greatest integer function, written in a squared bracket like this. How do you define it? That it is 0 when x is greater than equal to 0 but less than 1. And it is 1 when x is greater than equal to 1 but less than 2. We need only this part of it. Because he says, and then we have to verify, does FOG and GOF coincide in the interval 0, 1? He says then whether FOG is same as GOF on the interval 0, 1. On the interval 0, 1. What type of interval is this? It is open on the left, that is x is greater than 0, closed on the right, but less than equal to 1. So we have to find out the composite functions FOG and GOF in this interval where x is greater than 0 but less than equal to 1. 1 is included, and similarly GOF, and we have to see whether the two are equal, whether the two coincide means are equal or not. Let me take first the function FOG. FOG on x. FOG on x means f of gx. Now what is function gx? Gx is function modulus x. So f of, I'm sorry, not modulus x, g is greatest integer function x. So it is f of greatest integer function x. Now we have to find out the value f of g when x is greater than 0 but less than equal to 1. You know, this greatest integer function already we have defined. When x is greater than 0 but less than 1, it is 0. When it is, what is the value of this greatest integer function? It is 0 in this interval, or what is it, x is equal to 1? When x is greater than equal to 1 but less than 2, it is 1. So that means inside the bracket, this greatest integer function in the given interval this may take value 0 or 1. And now let's see what is the f image of 0. He says at 0 it is 0, so it is f0 is 0. f0 is 0. And what is f1? He says it is 1 when x is greater than 0 and 1 is greater than 0. So f1 is 1. So finally, FOG of x in the given interval may take value 0 or 1 in the given interval. And now find the other one, that is GOF of x in the interval. In the interval again, x is greater than 0 but less than equal to 1. Greater than 0, less than equal to 1. Now this means G of fx. You know, here in any case, x is greater than 0. What is the definition of fx when x is greater than 0? It is 1. It is 1. Look at the definition. When x is greater than 0, whatever on the right side it may go, it is 1, fixed. And now what is g1? g1 means the greatest integer function. g1 now means the value of greatest integer function at 1. You know, when x is greater than equal to 1 but less than 2, greatest integer function is 1. So it is 1. So what do you find? That FOG is 0 or 1, whereas GOF is only 1. So naturally the two are not equal. So we find that FOG and GOF, the two composite functions, does not coincide or are not equal. We have to find out the number of binary operations on the set AB. Let me call it A. AB. What is the number of elements in the given set A? It is 2. So what is the number of elements? Because when we say binary operation, so binary operation is always from A cross A to A. A cross A to A. So what is the number of elements in A cross A? A consists of 2 elements. So the number of elements in A cross A will be 2 to the power 2, or 2 into 2, that is 4. So now if a set consists of 4 elements, then the number of binary operations will be 2 to the power 4, that is 16. You may note a formula for number of, though this sum has been done, and this is your B choice, by the way, please note down. But further you may note down the number of binary operations on a set A, which consists of n number of elements, n is n. Then the number of binary operations is n to the power n square. Like in the present case, n is 2. So it is 2 to the power 2 square, that is 4. 2 to the power 4, that is 16. So remember the formula, it is n to the power n square.